There. Recording. Okay. Now we're on. Alright. Yeah, my smartphone's not really working too, so I have to use that to change pins. Alright, so for the do now today, I want you to try the first one, see what you get. I don't know that you're going to be able to get the second one, because we will be going back to yesterday's notes. But you can do this first one, and I also think you can do the one underneath that, the review of finding limits graphically. Is that the whole first one? Yes, it is. Alright, they're doing the do now. Okay, so for our first problem in the do now, the first thing you should have tried to do, get that plug in the 2, which is the x. When you do that, what do you get? 0 over 0. Oh yeah, this is going on today. This is today's problem. Okay, so when you do that, you get 0 over 0. So we know what's going on with the graph. There's a hole, so does the limit exist? Yeah, it does. How are we going to get it? That's right. Factor, cancel, substitute. So what about the factors for the numerator? Anyone want to volunteer what those are? Matthew. Right? Yeah, you got to give me both factors. X squared plus 2x plus 4. Nice. Factoring difference, 2 cubes. Here. Alright, so we factor, cancel. And when we substitute now, what do we get? Well, excellent. Show you that. Good job. Next one. You know what? This one is the one I don't even know if I got finding limits of x approaches infinity yesterday. Did I? So hold off on it, because I'll go back to yesterday's and I'll do that. In fact, maybe I should pause right now. Go to yesterday's, finish that, and then we'll come back here. You're going to have to remind me how far we got. I know I did too far. Let's see. Day. Right before it goes to say. About the two sides. Got a graph. That was all good. Got that one, but that was good. Did we do these, all 5 of these? Okay, cool. Then maybe it was like right here? Perfect. Nice. So you want to look at your day 6 notes and get to this spot. Does everyone know where we are? Yeah? Alright, good. This is important in understanding how to find limits as x approaches positive or negative infinity. If you have 8 and you divide it by x is a number that's growing, growing, growing. It doesn't sit still, so maybe think of it as being 1. Go back to this. So you think of x as being 1, and then maybe it's 10. So it was 8 over 1, say, now it's 8 tenths, 0.8. I'm going to keep making this denominator greater. Now it's 8 100, 0.08. It's growing though, it's never growing. Now it's 8 1000, 0.008. And if I just keep going, if I keep making this denominator larger and larger and larger, if I keep going forever and ever, what's happening with the value of 8 over x? It's getting smaller and smaller. Look, you can get as small as you want it to just by going out 4 digits down here, right? So what do you think the limit is? 0. Because no matter what, if you gave me any positive number, if you had said 0.1, I could say, nope, I could get closer than that, just by making the denominator larger. Any value you said that was more than 0, greater than 0, I could disprove it. I could find a denominator greater. So yeah, this limit is 0. Take a look at one of these. Suppose I want the limit. This time x is going to approach negative infinity, and of 3 over x. So we're taking 3, and we're going to put it over denominator. It's getting more and more negative. Maybe it starts at like negative 3, negative 3/10, negative 3/100, negative 3/1000, negative 3/10,000. See what's happening with these values? This fraction as I get closer, as the denominator gets larger and larger in the negative sense, what's happening to the values? It's 3 over negative a million. 3 over negative a million. Yeah, the magnitude is still getting smaller, so, and what number are they approaching? Still 0. If you think of the number line, that might help you a little bit. So, when you start out like putting negative 1 in for x, it's negative 3. But then when you keep making the denominator more and more negative, it makes the value of 3 over x, I'm trying to show you going over here, closer and closer to 0, which is coming into this side this time. So it is also 0. So yes, this one is 0. So what we can gather from this is that if you take the limit of a constant, a number that's not changing, 57 or negative 53, whatever it is, over x, and x is approaching to positive or negative infinity, what do you think the limit's always going to be? 0. As long as the numerator is not changing, even if it looks like a pretty large number to you, like 1,000 up there, 1,000 over infinity, that's going to approach 0. Yep. If x was approaching infinity, and that made the denominator approach infinity, yes, then it'll still be 0. Okay. Last year you guys talked a little about end behavior. Remember we studied polynomials? And you used to remember the cases, like the exponent, if it was odd or even, right? The odds, different in behavior, and then if the leading coefficient is positive up on the right. All those cases. Well, we can think about it in terms of limits. When you have a polynomial, there are only 2 different cases, only 2 possibilities for that end behavior. If you have a polynomial, what's one possibility for the y at one of the ends? Positive infinity, right? And then the other possibility is negative infinity. So when you want to determine which one you have, just look at the sign of the leading term as x approaches. Remember, it's approaching. So if x is approaching positive infinity, is x cubed positive or negative? Positive cubed. Positive. That's telling us on this graph, on this cubic, that as the x-coordinates approach positive infinity, the y's are going to shoot up to positive infinity. And if we look at the other end, if we look at the y values, as x approaches negative infinity, again, look at the leading term. A negative number cubed, negative infinity. So it's saying as the x-coordinates approach negative infinity, the y's are also approaching negative infinity. So when I graph this cubic, you'll see it's going to go up to the right because as x approaches positive, the y's going to go up. Okay. I'll go back to the more questions after I do finish this little guide. When you're asked to find the limit as x approaches plus or minus infinity, and it's of a rational function, there are 2 ways to do it. I'm going to show you the way where the case weight comes from. You probably memorized the cases last year. I'm going to put the same problem up here. Suppose I want the limit as x approaches infinity of x cubed minus 4x plus p over x minus 2x cubed. It's not like you just plug infinity in. So you're not like infinity. What you do, one way is to divide true by the highest power of x. Did anyone learn it that way? No, I didn't. Was that you never did? Oh, you never took the limit as x approaches positive or negative infinity? Oh, okay. Well, I'm going to show you. You still love it. What you do is you find the highest power of x. And in this case, it's x. What is the highest power in this case? X is the third. And what you do is you just put every term over x to the third. You're allowed to do that because what you're doing this, you're multiplying by 1 basically. If you multiply top and bottom by 1 over x cubed, x cubed minus 4x over x cubed plus 8 over x cubed. Down here we have x cubed minus 2x cubed. I am allowed to do that and make it look like a mess because what I've really done is I've multiplied top and bottom by 1 over x cubed. Multiplied by 1 over x cubed times 1 over x cubed. So when x is approaching plus or minus infinity, you can do this and clean it up and then take the limit. Let's just clean it up. Let's write it simplified. Some of these terms here. Simplify. X cubed over x cubed. What's that? About 4x over x cubed. Make it up a little better. 4 over x squared. Good. And then 8 over x cubed. Can't do that. One of the x's cancels. No problem. Down in the denominator, we can simplify the first term. 1 over x squared, and then it'll be minus 2. Okay. So we divided through by the highest power of x. We simplified. Now let's take the limit. And the great thing about limits, you can take the limit of each term separately. What is the limit of 1? Think about the graph y equals 1. As x approaches infinity. What are the y's staying at? 1, right? So this is going to be, I don't know why I'm thinking about the percentage, 1. Minus the limit of 4 over x squared as x approaches infinity. What do you think that limit's going to be? 4 over x squared, but x is approaching infinity. 0, right? 4 over infinity squared. 4, the numerator stays stuck at 4. The denominator's growing and growing and growing. That fraction is approaching 0. What about the limit of 8 over x cubed? If 8 is approaching, if x is approaching infinity. 0. Right? Anytime you have a number over infinity, it's going to be 0. In the denominator, what are we going to have? That's right. 0 minus 2. So we found the limit of each term separately, and now when we clean it all up, what is this equal? Negative 1/2. I don't think you're going to do it this way because it takes a little time. You probably, for the people that did study this last year, you probably remembered a cute little trick by considering the degrees. Numerator and denominator. So this is the same problem. Then remember what you do, like if the degrees are the same, which they are, Matthew? Yeah. If the degrees of the numerator and denominator are equal, then the limit will equal the ratio of the leading coefficient. The leading coefficient up here is 1. The leading coefficient down here is -2. Because it's the coefficient of the highest power term. So we just get 1 over -2. Same answer that we got before. But the reason it works like that when the degrees are the same, the degrees are the same, is because when you divide through by that highest power and take the limit, all the other terms are going to be 0. That's why it works. Now there's some other cases we have to just go back and look at. Let's say I'm taking the limit of a rational function as x approaches, and this works for either positive or negative infinity. If the degree of the numerator, I'm calling p the little p, the degree of the numerator, if the degree of the numerator is less than the degree of the denominator, so the highest power of x here imagine if you did divide through by x cubed and then took the limit. What you're going to get? If you divided every term by x cubed and then took the limit, what are you going to get as the numerator? Yeah, it's going to be 0 because these terms, after you divide through by x cubed and take the limit, that's going to be like 0 plus 0. But down here, you're going to have a 1 minus 0. So the 0 over a number that's not 0. 0 over anything else is always just 0. So every time you take the limit as x approaches positive or negative infinity of a rational function, if the degree of the numerator is less than the degree of the denominator, that limit will always look. So that's telling you that as x approaches positive or negative infinity, the y's are approaching 0. What does that mean as far as horizontal axis? You have one. You have a graph, and you go out really far. The y's just start touching the x-axis. What is the equation of the horizontal asymptote then? Y equals 0. The second case, if you're using comparing the degree method, is when the degree of the numerator and the denominator are equal. And that's the case we just covered. Remember how to do that? So what would this one be? What would this limit be? Degrees are equal. Remember, we take the ratio of the leading coefficient. 1 over 2. So that's telling you as the x's and y's go to either, as the x coordinates either go to positive infinity or negative infinity, the y coordinates are getting closer and closer and closer, in this case, to 1/2. So what would be the equation of the horizontal asymptote? Y equals 1/2. Last case. Sometimes they have a rational function, and the degree in the numerator is greater than the degree in the denominator. Okay. In this case, if you divided through by x squared first, and then took the limit, do you see what you would get? You divided every term by x squared, and then took the limit as x approaches infinity. Yeah, you'd have 1 over 0. 1 over 0.00000. That's going to always be, in this case, either positive or negative infinity. Okay? You know that with these graphs, it's going to look like the graph y equals x in the end. But the way you determine which, when the degree of top is greater, the answer will always be either positive or negative infinity. You look at the sign of the leading term. Either positive over positive or negative over positive. So the answer will always be positive or negative infinity when the degree of top is greater. Point. I'll go to that thing again. The way you determine what's to be positive or negative infinity, you say, okay, if x is approaching positive infinity, is numerator positive or negative? Positive. And what about the denominator? Just the leading term. Positive. So you have a positive over a positive. In this case, positive infinity. But it's really, technically, the limit doesn't exist. But we say, that really tells about the graph saying that. So when the degree of top is greater, the limit doesn't exist, but when you were asked for it, you're going to say either positive or negative infinity, depending upon the signs of the leading terms. So in this one, since the y coordinates are going off to infinity, does it have a horizontal asymptote? Yeah, that was just this. So that's the thing that you want to remember when you're taking the limit of a rational function. Let's just go through the three cases, make sure that we have it. So what happens if the degree up top is less? What is that limit always going to be? Zero. And what is the equation of the horizontal asymptote? What if the degrees are equal? What's that limit going to be? How do you get it? Ratio of the leading coefficient. horizontal asymptote? Yeah, it's going to be y equals whatever that ratio. If the degree in the numerator is greater than the degree in the denominator, technically the limit doesn't exist, but we'll always write one of two answers. What is the answer always going to be? Positive infinity or negative? It's always going to be positive infinity or negative infinity. And how do you tell which one? I guess I should have put that over here. How do you tell which one? Signs of the leading term. So you're going to look at signs, look at the signs, leading terms, to tell which one of these is going to be. So it will be always positive infinity or negative infinity. Okay. Now we'll get back to today's answer question. Here. Oh. Actually, try the second two now. Then we'll do that though. Might as well now. Because it's one of these. Find the limit to rational function next to which infinity. Anyone think they got it? Positive infinity. You guys see that? Degree of top greater, so you know it's positive or negative infinity. In this case, it's going to be positive infinity because both numerator and denominator would be positive. Now I'll do the whole story. So I have to give you the answers to which number? Look. Okay, a little bit better. What? 22? 22. Now I'm going to blow it up for you. Well, actually, this fits, but I don't know if you can read it. 16, I'll just read it for you. 16D, 17C, 18A, 19 does not exist. 20 is 4 pi to the 7th. Oh my gosh. 21 is 0. 22 is negative pi. It's negative pi. What's wrong with me? Negative infinity. Hello. Yeah. 16. Okay. I'm going to go up that. You got these answers now? Okay. So 16 is the first one to look at. Because the order doesn't matter. 16. Yeah, 16 was tough because, alright. Yeah, that's like going to infinity. Like, what is that? With this one, this is something you would need to combine that into a single fraction. Then you're going to love it. How do you combine two fractions into a single fraction? What do you need? Common denominator. Do you know what that common denominator would be? X squared plus x, right? Because that has the factors. That's just x times x plus 1. But that would be a good common denominator. So we would have, so we're going to combine them, and the denominator would be x times x. The limit is x approaches 0. Now I got to change the numerator. This one was fine. This is just minus 1, but that's like that. But the first fraction was 1 over x. So now it's going to, you have to multiply top and bottom by x plus 1, right? To get that common denominator. So it's x plus 1. See that? This is x plus, yeah, now the plus 1 and the minus 1, they're gone. Now we want the limit of x over x times x plus 1. What else can I cancel? X's, right? Because if you try to plug in the 0 now, before you do that, you're going to have 0 over 0. So then you would know cancel it. When you plug in 0 now, what do you get? 1 over 1. Yeah. You could if you didn't combine a lot of times limits, you just need to get it together. We haven't seen one like that. And you guys had 20 as a question, didn't you? 18 too? Okay. The 21, I wanted to look at that one first because 4 pi to the 7th, what does y equals 4 pi to the 7th look like? Y equals 4 pi to the 7th. It's fine, right? What does y equal no matter what x is? No, 4 pi to the 7th. Yeah, it has to be bigger than that. I put that in. Yeah, no, anytime you take the limit of a number that doesn't change, there's no x's in it, okay? It's just a horizontal line. And when you take the limit, it doesn't matter what x is approaching. That limit's always going to be that constant. Really? It's going to be bigger than that. But it's not exact. See, I don't like taking pi, which is a beautifully irrational number, and trying to make it irrational. That just makes sense. And then you said 18. Oh, I like 18. 18 is fun. Because when you try to plug in the 7, what do you get? 0 over 0. Not 0. We don't know what that is. So normally I say factor, cancel, sub. Now some of you might have been clever and figured out how to factor that numerator. Let's say you didn't. But even you could. I'll tell you after. But here's the thing. When you have a binomial that's contains radical, what do you just do? Square it. Then you're going to change things. But then you change it like so. Your salary is $1,200. Say, oh, can I square it? No, you can't do that. You know, you could multiply by 1 in this life or add 0. So yeah. Okay, what's that called? Square root of x plus square. The conjugate. Now, I'd like to multiply that denominator by the square root of x plus square root of 7 because we know when you multiply conjugates, the middle terms drop out. But I don't want to change anything. So what do I got to multiply the numerator by? Same thing. You're only allowed to multiply by 1 or add 0 or else you change. Now, the secret when you have to do this, distribute the binomial with its conjugates, but don't distribute the other one. So in other words, keep it x minus 7 times rad x plus rad 7 up here. Don't distribute it. You'll be so confused. But go ahead and distribute the rad, multiply out the rad x minus rad 7 times the rad x plus rad 7. And again, well, you know when you multiply conjugates, usually it's FOIL, but when you multiply conjugates, the middle terms drop out. It's just flip. FL. First, last. Right? If you multiply A minus B times A plus B, the middle terms drop out, you just get first. Yes, because when you multiply last, it'll always be positive and a negative if they're constant. So what is rad x minus rad 7 times rad x plus rad 7 equals? X minus 7. The beauty here? Now, if we tried to get the limit, we had 0 for 0. It's the conjugate thing. Now we're going to cancel. Plug in. Sorry, it's not different color. When you substitute in 7 now, after you cancel, you get rad 7 plus rad 7, which is what? 2 rad. As far as the homework tonight, you guys went up to oh yeah, you could do these infinity ones now. Now you know about the degrees. So actually, you could go up to, what do you think? Let me see, 31 is good. Let me see what 32 looks like. Oh, that's good. I think you can go to 35. Yeah, you can go to 35. So your homework tonight, make sure you got this down. It's finish to go do this worksheet up to 35. And we'll talk about the piecewise function limits on Monday. That's like the easy one. You have a lot of homework this weekend? Well, piecewise functions are they're easy with limits. I think you just gotta look at each of the one-sided limits and you got it. All right, let me stop this recording.